Welcome back to The Explainer. I am so thrilled you're here. Today, we're tackling one of the absolutely crucial challenges of our modern age, taming the ever-growing mountain of information. We're generating quintillions of bytes of data every single day. But, here's the reality. Having all that data means absolutely nothing if we can't make sense of it. That's exactly where our focus today comes in: data organization and distribution. We're going to look at how we take raw, chaotic information and turn it into something that actually drives decision-making.
I want to start by posing a really relatable problem. Just think about your own daily workflow for a second. As data volume grows, how much time do you actually lose just searching for unstructured information? The sources point out a pretty fascinating reality. As time passes and the sheer volume of your data grows, the time required to look for any piece of information from a source rises significantly if it hasn't been structured previously. You end up digging through a massive digital haystack just looking for a single needle. Actually, scratch that. It's more like a haystack that keeps doubling in size every day. It's frustrating, it drains productivity, and it's entirely avoidable.
Okay, let's dive into this. Here is our roadmap of how we're going to solve the problem of raw data together today. We'll cover 1. The chaos of raw data. 2. Defining data organization. 3. Structured versus unstructured data. 4. Data organization techniques. 5. The holistic data ecosystem. And finally, 6. Data as a strategic asset. All right, jumping into section 1, the chaos of raw data, and exactly why unstructured information is so challenging.
Fundamentally, raw data comprises variables observations. In its natural, unformatted state, it's essentially just isolated facts, numbers, or text strings. Because it's really just a collection of observations without any context or structure, it's incredibly challenging to deal with or analyze. I mean, think about it. A giant spreadsheet filled with millions of random numbers doesn't confer any meaning on its own. You literally cannot extract actionable insights from raw chaos. It desperately needs an intervention.
Which brings us right to section 2, defining data organization, or how we bring order to all that chaos.
So what does this all mean? Well, data organization is the classification of unstructured data into distinct groups, arranging it in a meaningful manner. The entire objective here is to take those raw variables we just talked about and put them into a format that actually makes sense. By classifying and grouping, we arrange the data in a manner that's easy to understand and manipulate. This is for sure the critical bridge between having meaningless facts and having highly valuable information.
To ground this high-level concept, let's look at a super relatable example from our sources. Think about a massive list of hundreds of test scores just jotted down on a blank piece of paper. That's completely unstructured. But if we arrange those students' grades into different topics, say mathematics, science, and history, we're applying data organization. And this brilliantly illustrates how a chaotic list of raw numbers suddenly becomes a meaningful performance report. You can instantly see which subjects a student excels in and which need work. It's like putting together a giant puzzle.
Moving on to section 3, structured versus unstructured data, and really understanding the difference between the two.
Now, what's really interesting about this contrast is how different these two worlds actually are. On one side, we have structured data. This is your tabular information. Think neat rows and columns. It can be readily imported into a database and immediately utilized by analytics software. It's tidy, it's ready for action. But on the other hand, unstructured data is regarded as raw and unformatted. Our sources compare it to a plain text document, where names, dates, and other pieces of information are just kind of dispersed across random paragraphs. It absolutely cannot be easily read by traditional analytics tools without some major processing first.
Let's move to section 4, data organization techniques, looking at how exactly unstructured data is transformed.
Okay, let's dive right into this. Our sources outline several foundational data organization techniques that help transform those messy, random observations into highly usable formats. First up is classification, which we touched on earlier, grouping data based on important categories. Then we have frequency distribution tables, which arrange data by quantifying all potential values and showing how often they occur. And finally, we have visual methods like image representations and graphical representations. Think histograms or pie charts. These techniques arrange raw data into formats that immediately provide visual insights, which literally saves analysts massive amounts of time.
Next up, section 5, the holistic data ecosystem, focusing on the IT and systems perspective.
As noted in the source material, IT workers utilize the notion of data organization in several essential ways. In the enterprise world, these practices are frequently grouped together under the broader umbrella term data management. And it's not just about software either. Data management also involves physical records, like reordering or assessing the physical arrangement of data components to ensure everything is streamlined and accessible.
But, the real magic happens when we deal with the really messy stuff. The analysis of somewhat organized and completely unstructured data is a crucial component of modern business data organization. A few highly specialized tech professionals have built technological tools and resources designed specifically to seamlessly manage and incorporate substantially unstructured data into a comprehensive holistic data ecosystem. This basically ensures that no valuable insight gets left behind, regardless of how it was originally collected.
Let's move to and see how this builds up to our final point in Section 6, data as a strategic asset, which is really the ultimate business payoff here.
So the crucial point is this: data sets are among the absolute most valuable assets possessed by firms globally across a huge variety of industries. Businesses don't just employ data organization methods for the fun of being tidy, right? They do it specifically to make much better, highly lucrative use of these vital data assets. Organized data drives market efficiency, it customizes strategies, and it fundamentally powers modern business. Because data is such a vital asset, executives and professionals prioritize its organization as part of a complete holistic strategy. By diligently examining both organized and unstructured data, executives are generally aiming for three primary goals. First, to expedite business operations, making sure things run faster and smoother. Second, to boost business intelligence by acquiring superior, actionable insights. And third, to enhance the business model as a whole. It's all about leveraging every single byte of information to stay competitive. Which brings us to our final thought for this explainer. I want you to look at your own operations for a minute. Is your holistic strategy successfully turning raw chaos into your most valuable business asset? Or are you still losing precious time searching through random paragraphs and unstructured numbers? The techniques and the ecosystems are out there to transform that raw data into a real strategic powerhouse. It's just a matter of executing the right organizational strategy.
Have you ever stared down a massive, chaotic spreadsheet full of raw numbers and just felt totally overwhelmed? Well, today, we're going to explore exactly how to transform that chaotic raw data into powerful predictive statistical models. Think of this as your personal guide to becoming a real-world data detective, taking completely unstructured numbers and organizing them to quite literally predict the future.
Here is our roadmap for today. 1. Organizing the data chaos. 2. Decoding data distributions. 3. Understanding discrete data. And 4. The 4 discrete models. Let's dive right into Section 1, organizing the data chaos and making sense of all those numbers.
Imagine an analyst goes out and gathers 500 raw data points tracking machine runtimes on a manufacturing shop floor. Now ask yourself, what good are those individual numbers to management if they aren't actually categorized? The truth is, staring at a massive list of 500 unformatted numbers tells you absolutely nothing about the health or efficiency of that factory. It's just noise.
So, the absolutely crucial point here is that unstructured data must be arranged into usable formats. The data distribution approach takes this raw chaos and shapes it into graphical representations, things like histograms, box plots, or pie charts. Only then does it actually start giving us relevant information. It's really all about grouping those variables so we can finally see the big picture.
Moving right along to Section 2, decoding data distributions and finding the hidden order. Okay, so any population with dispersed data is categorized as a distribution. Essentially, this identifies all the potential values for a variable and shows their relative frequency, meaning the probability of how often they actually occur. The primary benefit here is incredibly powerful. Data distribution allows us to estimate the probability of literally any certain observation within our sample space. Taking that a step further, we can build a probability distribution. This is a mathematical model that determines the exact probabilities of specific test or experiment outcomes occurring. We use these models to specify distinct sorts of random variables, whether they're discrete or continuous, so that management can actually make an informed choice rather than just guessing in the dark.
Now, depending on the category of the random variable, an analyst can employ a pretty diverse toolkit of statistical approaches. You can look at the mean, the mode, the range, or the probability. But to use these tools effectively, you have to establish the population's distribution type first. You absolutely need to know what kind of data you're dealing with before you start crunching numbers.
All right, Section 3, Understanding Discrete Data and the Power of Countable Variables.
Discrete distributions focus entirely on finite outcomes that you can literally count. Unlike continuous data, which can take on an unlimited number of values on a measuring scale, discrete distributions deal with clean-cut things. Think rolling a die or counting the number of heads in a coin toss. You can display discrete distributions perfectly in tables because the values of the random variables are distinctly countable.
Finally, Section 4, the 4 discrete models, which make up your essential statistical toolkit.
Playing the role of a data detective, let's look at the first model on our list, binomial distributions. This is one of the most fundamental models in statistics, and it deals with attributes categorized into exactly 2 mutually exclusive and exhaustive classes. Think of binary scenarios. The binomial distribution quantifies the chance of getting a specific number of successes versus failures. This applies perfectly to things like tracking the exact number of acceptances versus rejections on a factory assembly line. The key is, the trial must have exactly 2 possible outcomes.
Let's look at the classic coin toss. The likelihood of falling on heads is 1/2, and tails is 1/2. The vital rule for a binomial distribution is that the probability of success is perfectly constant. It is exactly the same in every single trial, no matter how many times you flip that coin.
Next up is model number 2, the Poisson distribution. This one is super fascinating because it looks at events happening in a well-defined order or within a specific given time period.
This model is used for attributes that could potentially take on huge values, but in everyday practice, they usually take on tiny ones. It's an incredibly useful model for tracking events over time where the occurrences are random, but they still have a known average rate. For a real-world analyst, the Poisson distribution is your bread and butter for tracking critical but infrequent events. If you want to model the number of manufacturing flaws, factory accidents, or even worker absentees over the course of a month, this is absolutely your go-to tool.
Our third model takes us to the hypergeometric distribution. This one assesses successes from a sufficiently large population, but there is a major catch with how we actually sample the data.
The key catch here is the phrase, without replacement. You're assessing the chance of successes in a certain number of trials, drawing from a large population, but you aren't putting the items back once you draw them.
So let's quickly compare this back to our first model, because they seem similar but have one critical mathematical distinction. While a binomial coin toss always gives you a half chance no matter what, the hypergeometric distribution changes the odds for every subsequent trial. Because you are drawing without replacement, the population physically shrinks, and the probabilities shift every single time.
And finally, we have the fourth tool in our discrete data toolkit, the geometric distribution. Basically, this model is all about the waiting game. Instead of looking at a fixed number of trials, the geometric distribution assesses the probability of the occurrence of the very first success. For example, imagine a marketing rep randomly picking hockey players from several different institutions. They're going to keep picking and picking until they finally discover an Olympic participant. The geometric distribution models exactly that wait time. Comparing our big 4 discrete models side by side here, we can really see how each acts as a totally unique statistical lens for predicting specific outcomes from countable data. Whether you're tracking consistent binary outcomes, random events over time, shifting probabilities without replacement, or just waiting for that very first success, there is absolutely a model here to structure your raw data.
So, now that you understand how to organize the chaos of raw numbers into actionable probability distributions, think about your own daily work. Which of these 4 discrete models could you literally apply tomorrow to predict an outcome, streamline an operation, or prevent a critical failure? The data is out there, just waiting for you to find its hidden order.
We've got a really fun visual journey lined up for you today. We're going to dive right into the mathematical shapes of data. You know, if you've ever stared at just a massive, endless spreadsheet and wondered, how on earth do data analysts make sense of all this chaos? Well, the secret usually lies in understanding the actual shape the data takes. So today, we're taking a little gallery tour of continuous distributions. We'll look at these shapes, break down their unique traits, and figure out what they're really telling us about the world. Let's jump in. Real quick, here's the roadmap for our tour today. First, the shape of continuous data. Then, the classic normal distribution. Number 3, log normal and F distributions. 4, chi-square and exponential. And finally, the t-student distribution. Starting off with Section 1, the shape of continuous data and its unlimited potential values. Okay, so think about how we usually gather data.
A lot of times, it's discrete, meaning there's a finite, set number of outcomes, like rolling a die or counting heads in a coin toss. It's a simple, straightforward count, right? But what happens when your data points don't just stop at a simple count? What if you're measuring something like weight, or time, or physical dimensions, where the values can land absolutely anywhere on a sliding scale? Basically, how do you even measure a data set that has unlimited possibilities?
Well, that brings us to a really important definition, the continuous random variable. This is a random variable with an unlimited and completely uncountable set of potential values, and it's represented on a continuous measuring scale. It is so much more than just a simple count. Imagine an analyst grabbing 500 random measurements off a factory floor. On their own, those numbers don't really help management at all unless they're categorized or organized into something useful. We need a way to wrap our heads around this uncountable infinity. And that is exactly where the probability density function, or PDF, swoops in to save the day. You can think of the PDF as our lens. Since we obviously can't count an infinite number of exact values, the PDF steps in to describe the overall characteristics of that random variable. When we plot these out, we normally see a clustered frequency distribution start to emerge. Basically, the data points clump together and form a distinct, recognizable visual profile.
I love this quote from our source material because it just hits the nail on the head. The probability density function views it as the distribution's shape. It's brilliant. By plotting all those infinite possibilities with a PDF, we're literally giving the data a physical form that we can actually look at and analyze. So now that we know how we see the data, let's go look at the most famous shape in our gallery.
Moving to Section 2, the classic normal distribution, also known as the Gaussian curve.
You've definitely seen this one before. It's the Gaussian distribution, better known as the iconic bell-shaped curve. As you can see, it has a much greater frequency, or probability density, clustered right around that core, center point. In the real world, when you have features that are expected to fall on either side of a target value with equal likelihood, they adhere perfectly to this normal distribution.
But notice what happens at the edges. As those values move away from the center point on either side, the frequency drops off dramatically, so the vast majority of your outcomes are clumped right in the middle. And extreme outliers, they become exceedingly rare. It is just beautifully symmetrical. But as we all know, real-world data doesn't always behave so perfectly.
Which brings us to Section 3, log normal and F distributions, dealing with asymmetric data shapes.
First up in this room is the log normal distribution. This happens when a continuous random variable x follows a distribution where its natural logarithm actually forms that normal, bell-shaped curve we were just looking at. And here is where it gets really cool, almost like statistical magic. As your sample size rises, the distribution of the sum of these random variables actually approaches a normal distribution, completely independent of how the individual variables were distributed.
Right alongside it, we have the F distribution, and this one boasts some pretty quirky traits. First, it's totally asymmetric. It has a strict minimum value of 0, but get this, absolutely no maximum value. It just stretches out endlessly, approaching 0 but never ever actually touching that horizontal axis. In practice, analysts use the F distribution a ton to examine the equality of variances between two normal populations. It's basically a highly specialized tool for comparing how spread out different data sets are.
All right, Section 4, chi-square and exponential, where we look at squaring variables and constant rates. So a really crucial thing to understand here is how distributions can actually be built out of other distributions. Take the chi-square distribution, for example. This occurs when you take independent variables that have a standard normal distribution, you square them, and then you add them all together. Imagine an equation like y equals z1 squared plus z2 squared, and so on. Because we're squaring them, the resulting distribution is constrained below 0, meaning it never drops into negative numbers. It's symmetrical, and beautifully, just like we saw earlier, as the number of degrees of freedom grows, this chi-square shape eventually morphs right into that classic normal distribution form.
Then we have the exponential distribution, which is incredibly common. Because its form characteristics stay completely constant, it is used all the time to represent products that have a consistent failure rate. It's also really closely connected to the Poisson distribution, basically linking the continuous measurement of time with specific discrete events.
Finally, Section 5, the t-student distribution, the ultimate stand-in for the normal curve.
Let's look at how the normal distribution compares to the t-student distribution. We already know the normal curve relies heavily on knowing the standard deviation. But what do you do when you're analyzing a population and that standard deviation is just a total mystery? Well, you can't use it.
That is exactly when the t-student distribution steps in. It's essentially the ultimate substitute or understudy for the normal curve.
The t-student beautifully mimics our gold standard. It has that symmetrical bell shape around its mean. Data analysts use it constantly for testing hypotheses and building confidence intervals for means. And it really reinforces a fundamental rule we've kept seeing throughout this whole gallery. When random variables are averages, the distribution of that average tends to be normal, totally independent of the distribution of the individual points. It all just circles back to that one central reliable shape.
Well, we've reached the end of our gallery tour today. We've seen how continuous distributions, from the perfect symmetry of the Gaussian curve to the endless tail of the F distribution, right down to the super practical t-student, really give form to uncountable infinite possibilities. By clustering those frequencies into probability density functions, we get to transform abstract, chaotic numbers into clear visual narratives. So I want to leave you with this one final thought to ponder. Now that you actually know their shapes, what is your unpredictable data trying to tell you? Thanks so much for hanging out with me for this explainer,